Welcome everyone to the AAVSO webinar series. My name is Bert Pablo and I am the staff astronomer at the AAVSO. It's great to see all of you here today. We're going to hear a great presentation from Dr. Andrea Dupree on Betelgeuse. But before we dive in, I have a few quick announcements to make. If you've been here before, you know the drill. We have first, a quick tour of Zoom webinar. If you take a look at the bottom of your Zoom window, you will see a few buttons. There's the chat box, where we've all been introducing ourselves. There's the CC or Show Captions button, which allows you to enable or disable Zoom's automatic closed captioning. And there's also a special button labeled Q&A. If you click the Q&A button, you will have the option to submit questions for our presenter. You can submit as many questions as you'd like at any point during the presentation. Don't worry, it won't interrupt the speaker. After the presentation, we'll have an extended Q&A section where we will try to answer as many of your questions as possible. Please note, if you have questions, to ask them at the Q&A. If you ask them in the chat, it's very easy for us to lose them and we will not see them. I'd like to express gratitude at this point for our series sponsor, Boise Astro. Boise Astro provides online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out their website, boiseastro.org, to learn more about their offerings in astrometry, photometry, and spectroscopy. Support from sponsors like Boise Astro and our donors make the work of the AAVSO possible. To support the AAVSO, please consider a donation by scanning the QR code on your screen or going to aavso.org. All donations are tax deductible and support our mission of enabling anyone, anywhere to participate in scientific discovery through variable star astronomy, now and for generations to come. And finally, it is time for our presentation today. Dr. Andrea Dupree is a senior astrophysicist in the Solar, Stellar, Planetary Sciences Division of the Center for Astrophysics at the Harvard Smithsonian. Her research focuses on spectroscopy of stars and the interstellar medium. She participated in science teams for IUE, EUVE, FUSE, and Kepler. She obtained the first direct image of a star other than the Sun, Betelgeuse, with the Hubble Space Telescope, and in 2020 documented the historic great dimming of the supergiant with spatially resolved ultraviolet spectra, discovering a gigantic chromospheric outflow event. She is known for studies of young accreting stars, atmospheres of luminous stars, stars in clusters, mass loss, and stellar winds. And with that, I would like to let her start her presentation. One final note, a couple of you raised your hands. There isn't really anything we can do with that. If you have a question, please just ask it in the Q&A part, and we will get to it as soon as we can.
Okay, are we ready to go?
We are.
We are. Let me share my screen. Thank you for that lovely introduction. I believe you can you see my screen now?
We can, yes.
You can. Okay, great. We're ready to go. I'm going to talk about Betelgeuse, an exciting star that never ceases to amaze us. And as a matter of fact, I'd like to start way back and point out how it has been important and a part of civilization and all of us for a very long time. Whoa, wait, we got to go back one. No, something has happened here. This isn't right. Wait a minute. Previous. There we go. If you look in the southeastern part of France, you will find that the caves in the Lascaux caves, so-called, there are prehistoric paintings. And actually, you can find the outline of Taurus the bull, the Pleiades, and of course, Orion and Betelgeuse. And then even a Korean star chart, which was based on a map centuries before, showed the outline of the Orion constellation. And over a century ago, the New York Times, above the fold, highlighted the first measurement of the diameter of the star other than the sun, and that is, of course, Betelgeuse, where they called it the Colossus of the skies. I thought it was wonderful. It even appeared above the fold in the New York Times. And that measurement, which was made at Mount Wilson by putting I-beams out the sides of the 100-inch telescope and then using it as an interferometer, that measurement still holds good today. It's still confirmed by contemporary measurements. So that's pretty exciting. Okay, what's Betelgeuse doing right now? Well, it started out as a massive star. It's much more massive than the sun by about 15 to 20 times, and it's much hotter. It was much hotter than the sun. But then, as the stars evolve, they start burning the fuel in the core of the star. And we think right now that the central hydrogen fuel has run out, and when this happens, the core contracts and the star begins to expand, and you can see moves across. This is a little diagram that I'm sure many of you are familiar with. No, that shouldn't happen. No, sorry, this is doing odd things here. Okay, that shows. Let's go back a minute. I apologize. Okay, now I think we're going to be okay. The star is now in a evolved state. It's much cooler than it originally was, but as the nuclear fuel burns, the star then expands. So the star has become a sort of a bloated, huge supergiant star, as we call it, which has a radius about 1,000 times that of the sun. And then the outer surface has cooled down to several thousand degrees. The star is big. I mean, it's really big. It's one of the largest stars, larger than some of your other friends, Antares, Aldebaran, and everything, much, much bigger. And as a matter of fact, if you put it at the center of our solar system, the surface, that's the part that you can see, just like the surface of our sun, would extend out to the orbit of Jupiter. But there's even more. The outer atmosphere, which is hotter, it's like our solar corona, although not at those high temperatures, but it extends at temperatures of about 20,000 degrees out to, beyond the orbit of Neptune and beyond, 3 to 4 times the optical surface. And this we observe in different ways with millimeter wavelengths or in the ultraviolet where we can see that. Now, why do we care? Well, first of all, it's large. And it's nearby, or it's nearby making it large, but it's large to begin with. And we can resolve the surface. I mean, this is unique. Other than the sun, which is a dwarf star, a small star, we're seeing a completely different flavor of stellar surface. And one of the things we're very interested in is how stars lose mass. And this way, we can observe it directly. And mass loss is very important. It affects the evolution of the star, how it will collapse, the supernova light curve that will result from the supernova because of the material that's been lost before it modulates the light curve, and the ultimate fate of the star, whether it might be a neutron star or a black hole or just a white dwarf. So mass loss is very important. It also regulates the enrichment of everything in the universe. I mean, all the heavy elements that are made inside stars become part of the interstellar medium and part of the cycle of the stellar evolution. And now, as many of you have probably heard, it may have a companion. So I'm going to talk about several of these things. Let me start out with a little lesson on what we're seeing. The size of Betelgeuse depends on the wavelength that we use. I mean, if we're looking in the optical or in the infrared, we see a small circle of a small diameter star. The submillimeter takes us out to higher layers, but the ultraviolet takes us out to even more substantial layers, higher in the atmosphere. And so by using observations at these various wavelengths, we can watch phenomena in the atmosphere, we can see how the atmosphere changes, and that gives us a lot of insight into the whole process of mass loss and the structure of the atmosphere that we're looking for. Now, we did make the first direct image of the surface of a star other than the sun, and that was Betelgeuse, and that was using a camera. When I say image, I mean really like a camera, and it is a camera. It was a camera. We're not reconstructing it. We're actually taking a picture. And that was where we realized for the first time that in the ultraviolet, it was 3 times larger than the optical. And we also found this huge hot spot in the southern part of the star. And subsequently, with new techniques and other techniques in the infrared, all of these variable hotspots were seen. You see on the left, there's an image showing 2 bright spots. There's a center simulation that is made that reconstructs or attempts to simulate the presence and the appearance of these spots. And on the right, there's some time sequences showing that in these spots, at least over this period of 3 to 4 years, I guess it was, the surface changes, the spots change. These are convective spots. We looked at it again for another 4 years with the Hubble Space Telescope, and we could see that even in the outer layers, and this is above the surface in the ultraviolet, the ultraviolet emissions vary. This set of exposures taken over 4 years, I should point out the one in the upper left corner, that's a hot white dwarf. Just to show you, oh, there we go again, and we're having problems. Sorry. Just to show you again that the HZ4 is a white dwarf, and it's a small single star. And so that's what a point source looks like to the Hubble Space Telescope. But you can see that the subsequent images taken in the next 4 years look much more extended, and the appearance of the hotspot, these are all taken with the same exposure time. So the appearance of the hotspot changes quite dramatically. Okay, and now simulations have also been made of the hydrodynamics and the convection, which can reproduce the small convection cells in a star like Betelgeuse, but as far as I know, they haven't gotten to the larger ones. And what we have seen subsequently indicates that some are substantially larger than this sort of boiling gas on reminds me of chocolate syrup on the stove or something with these convection cells. Okay. Now, in the UV, we can also do something that's very useful and instructive, and that is we can use a very, very small aperture in an image, and we can then scan this small aperture across the surface of the star. This is one of the early ones with a big, large square aperture that you see on the left. And we can take a spectrum at each one of these positions, and you see marked by the white dots in that sort of T-shaped pattern. And that's where we could infer the motion of the gas and define the orientation and the rotation of the star. And that's where we saw the hotspot, and that appears to be on what we believe to be the pole. I'll use the word south. I guess it's really the southwest pole. It appears in the southwest of Betelgeuse. And so we were able to determine the orientation as well as the rotation. And something very surprising happened. We discovered that it was rotating much more quickly than it should be, with a period on the order of 30 years or so. And that's much more quickly than it should be if it were just, when you think about a star that's on the main sequence and starts its life rotating very rapidly, and then as it gets larger, it obviously slows down. The inverse of a skater who pulls in arms in order to go more quickly. So it should be more slowly rotating. And that's a puzzle. ALMA, which is an array of millimeter antennas in Chile, on the Atacama in Chile, made a very nice image confirming all this axis rotation. And then they found a spot on the other side, which is really in the North Pole of rotation. And you see that yellow line marks the axis of rotation of the star. And you see that it's tilted about 45 degrees from the north towards the east. And then the circles mark molecular emission that they have also seen from, observed many times from this star. But now let's go to the optical, all of you AAVSO observers out there. The variability, as I'm sure you know, was first discovered or rediscovered, as they say, maybe 150 years ago. And the sequences, this is the from the archive, or dipping deeply into the AAVSO website, from about what 1894 up to 2019 or 2020, 2018, I guess. And what we've seen is that there are two periods in this optical variability. One of about 400 days, and that we understand to be what we call the fundamental pulsation mode of the star. That is, if you have a star of a given mass, it's just going to normally pulsate with a 400-day period. There was also an indication of a longer pulsation period, or variability period, of about 2,000 days, 5 or 6 years. And this has been a question for a long time, and we'll talk about that a little bit later. Okay, let me go into one of the exciting things that happened in 2019 and 2020, the so-called Great Dimming. And here we see the V magnitudes from the AAVSO, and you can see the nice repetitive 400-day, roughly 400-day minima as it proceeds from 2013 on through 2019. And then in the late years and late months of 2019, I wrote there, trouble started. And that's when suddenly the star started getting fainter. And oh my goodness, everything went crazy. There were the social media, the TV, people didn't know what happened. I remember going on one of the Twitter feeds, and they said, my calculations show that the star was going to explode tonight. And then it said hide. Now, I'm not sure what exactly you do. It did this, of course, 700 years ago. But people were very, very concerned because it had not been seen in Betelgeuse before, and we didn't know what was happening. And then the light curve shows you it became extraordinarily dim in early February of 2020. Okay, let me just remind you, the current state, according to theorists, is that it is fusing helium to carbon. So it's gone through 10 million years of evolution. We're in the middle of the helium to carbon stage. So I don't think it's going to be a supernova for a while. I don't think we're going to see it. You can see it proceeds on sort of shorter and shorter time scales as the nuclear reactions change, until finally you get into a very unstable phase. I guess it's the oxygen to silicon phase, when we expect the variability to increase before it becomes a supergiant. Okay, and it was actually a little bit before that, in 2018, when a group of us met at a meeting and decided that we could really learn something about Betelgeuse if we made a concerted effort with many types of equipment and telescopes and detectors to watch it and find out what is really going on and follow it at all these different frequencies. So we enlisted lots of people who worked on the ground and in the space with the Hubble Space Telescope, other space equipment, ground-based, and folks from the AAVSO. And we decided, okay, we're really going to follow this star carefully all these ways. And then the star performed well for us. So we feel very rewarded. Let me tell you what happened during this year in the life of Betelgeuse. I'm going to start in January of spring of 2019, when on the left, Miguel Monterrey, the postdoc in France, used a very large telescope of the European Southern Observatory. And on the left, he took an optical image of Betelgeuse, and it looks reasonable. I mean, there's a bright spot in one place, and there's sort of darkening around the edges, and that looks all reasonable. Now, the other thing that was going on at the same time that's very powerful is something called tomography. And that was being done by Catherine Kravchenko in Munich. And what happens is you take a spectrum, which I'm showing on the right, and you identify certain lines, and you know that they're formed in a particular layer, a lower layer of the star, and then inside the surface, below the surface. And then you'll find another set of lines that's formed perhaps a little bit above. And then you can find more and more different regions identified by these lines. And when they started looking at the motions of these between January and March, they found that shocks were developing. You could see the shocks moving out, and the surface began to expand. Okay, and the optical spectra that we got out at the Whipple Observatory in Arizona showed substantial changes in the outflow as well. You can see by looking at the peaks of these lines, the V and the R peak, that during the spring of 2019, that's the blue and the red line, that the asymmetry changes quite dramatically from what it was previously. Formerly, the V, the violet emission, was higher than the red, and this reversed. And that indicates that there's outflowing material that's absorbing the violet side of the line. So, oh my goodness, something is going on. And the radial velocity shows something very similar. This radial velocity data that's taken with an automated telescope on the island of Tenerife and the T80 Observatory by a group from the Leibniz Institute in Potsdam, and it's called Stella, and they've been monitoring the radial velocity for a number of years. And you see at the top arrow where we've marked in January and March in the spring, this is all 2019, the surface outflow starts. And then by the fall, at the bottom where the arrow is pointing, there's a very flat, a continuous outflow of material. And notice that's quite different from what happened in 2012, 2013, 2014, when the material the star is pulsating and the material went out and back in and out and back in. This time it was staying out for a much longer period of time than it had before. So something's going on. And in the fall, we were using the Hubble Space Telescope, again, taking spectra from different parts of the star, and we could find an enormous increase in strength in these magnesium lines, which are very characteristic of the very low chromosphere. And you see the red profile here is much stronger. That's in October, much stronger than the green one, which is barely peeking out of the February, the purple one. So in other words, in October, there was this enormous outflow of material, and we could also measure the density and discovered that it was much higher density than it had been before. So it's suggested to us that there's something came up from the photosphere and combined to inject material further out into the atmosphere of the star. And now we would take, Miguel went back again to take images from the European Southern Observatory and found that in December of 2019 on the right, look how different that image looks compared to January of 2019. Clearly, there's a big dark cloud, something in the southern part of the star, which we think is the formation of dust that happened as a result of the cooling of the material that was ejected that we saw. And remember that having this happen over a period of a year is perfectly fine. This is a big star. And when it is only moving, the material is only moving at 5 kilometers a second, which of course for astronomy, that's pretty slow. It's going to take 6 months, 7 months, 8 months to get out through the extent of the atmosphere of the star. So during this time also, the spectrum became much different, and the temperature, we could measure directly that the temperature on the surface was cooling. You see on the left, we see that oh, there we go again. Sorry. We see on the left the change in the spectrum. It gets weaker and weaker. Those deep absorption lines of a lot of the atoms in the photosphere, and that's the surface, are getting weaker and weaker, which indicates that the temperature is going down. And then we can measure it directly. The little red dots show the variation of a temperature diagnostic. And you can see how as the star becomes dimmer in the visible, the temperature also goes down, as indicated by this diagnostic. So what has happened? We saw in the spring, northern spring, January to March of 2019, that the surface outflow started from the optical spectra. And then in the fall, we could see from the ultraviolet spectra that there was a progression of dense material from the southern part of the star. And then in January, February of 2020, the surface of the star became lower density and became cooler. Dust formed because as the material moves out through the hot chromosphere, it goes to a cooler region. Molecules form, dust form, and then we could see in the near-infrared spectra and the optical image that indeed there was dust that was there. So it's a wonderful story that convection really drove this from the surface all the way out to the interstellar medium. This is we call a surface mass ejection, which we think was propelled by a large convective cell, probably at the right phase of the natural fundamental oscillation of the star, may be constrained by a magnetic field that left us with a cooler, less dense photosphere. And this was big. I mean, this might have been a quarter of the surface of the star. I mean, this was a big event. And it's the first time it's ever been observed directly, and the amount of mass loss we think is comparable to the amount that it normally loses during a year. So it was a new phenomenon that we could observe directly. Now, let me just compare this to what's called a coronal mass ejection. You may be aware of the fact that our sun, which we can also observe in great detail, our sun has these events that typically follow solar flares that are called coronal mass ejections. And you see one that's going on here. This little video runs for about 3 hours. So the time scale is quite different from what we're seeing in Betelgeuse. We're talking about months in Betelgeuse and hours and minutes in the sun. The size of what happened in Betelgeuse is much larger than this, which you can see here. It just occupies, I know, 1/100th of the solar surface. The mass loss was also much more substantial. And then the question is, what is the frequency? We know the frequency of coronal mass ejections can be quite high, weekly or maybe even more, depending on activity, magnetic activity, and flaring activity. But with Betelgeuse, this is the first one we've been able to see. Whoever, whoops, I guess, okay. So then we had to follow it. But as you know, what happens is that we lose sight from the ground. We generally lose sight of Betelgeuse because it goes too close to the sun. So we started using some new techniques to try to find it, which I thought were rather interesting. We realized that there's a spacecraft called Stereo, which is a solar spacecraft meant to look at the sun. And it's in Earth orbit, but it trails the Earth by about 2.5 months. That was in 2020. But that means that when we lose Betelgeuse from the ground-based telescopes generally, Stereo could see it. And they had a wide-angle camera, and they were very willing to turn off links to the spacecraft, rotate the spacecraft, turn over to look at Betelgeuse, come back again, and then send us the images from which we could follow the brightness. And you see here, we could see in the right figure, you can see the stereo plots indicated by little red stars. So when it couldn't be seen in June and July from the Earth, we could get a measurement from Stereo, and we could see that it did not continue to its expected magnitude on its 400-day period. That's indicated by the broken black line. And you see in July of 2020, there should have been the brightest phase, which didn't happen. But then moving on, some very clever people at the AAVSO among you figured out how to make observations, daylight observations, with a very, very small telescope, and I think it's a 250 millimeter aperture telescope, by taking isolating the sun, shielding it from the sunlight, and taking many photographs, and then combining them in such a way with other in comparison that they could then extract a very good, accurate magnitude measurement. And you see that on the left, where the stereo, the stars picked up right after the June to 2020. But then you see those open diamonds, the blue ones, that nicely fill in the parts of the light curve when normally we wouldn't expect to have it there. So that was very, very exciting and has continued. And there's yet more, and that is a Japanese graduate student discovered that the meteorological satellites, in particular Himawari 8, which is a Japanese geostationary satellite, takes its images hourly of the Earth using about 12 to 16 different filters in the optical and the infrared. And that's extremely powerful because that means that you can detect molecules, you can detect the general V magnitude of the star, and get other information that you can't get just from a V magnitude alone. And believe it or not, in the picture to the left shows you the meteorological image of the Earth, and that little red square marks where Betelgeuse is. And you could see it's right off the limb of the Earth, and they could follow it all the time when the satellite was operating, and they can actually get a number of stars near the equator, the celestial equator. We also have a similar set of satellites called GOES, which are NOAA satellites, making the same kinds of measurements. And we haven't looked at that data, but it's there and it's exciting. So there are lots of different ways that came to light after this great dimming of Betelgeuse. So now what's happened? Well, we can follow it up until this is the last measurement that I found on the AAVSO website, but you can see that the 400-day, that's the broken black line, the 400-day period is not there anymore. And that indeed it's missing that period. The outbreak, the great dimming, the mass ejection has changed the pulsation that we observe in the star in the in the optical that we're seeing. And there have been some people making simulations to understand what has happened. And let me share some of those with you. These are hydrodynamic simulations where we model a star. This is done by Morgan McLeod at the Center for Astrophysics. And he models the star. And in the interior, he adds a hot, dense, large region. And you see that on the left in the blue the blue, well, let me start back a bit. There are two images here. One shows the top set shows a slice in radial velocity, that's motion across, as if we cut the star in half, cut the simulation in half. And then in the bottom three ellipses show you what happens at the surface of the star. And you can see the scale is such that blue means outward motion. So you can see that at the beginning, on the first panel in the top panel, the first panel to the left, you can see that the outward motion from this dense material is below the surface, and about twice as long, 170 days later, it's moving out. And then finally, about a year later, it breaks out close to the surface. And you can see that in the images down below. It's perhaps more exciting to see it like this, where this rising plume that's coming out moves out, penetrates the surface, and then you can follow it, which he did. And we find that something called mode switching arises. I mean, what's happening is the first outbreak of that convective cell sends the outer atmosphere moving out faster. But meanwhile, the inside moves back down again, and the outside is still moving out, and then finally moves back down, so that you're getting a what we call mode switching. It goes into a higher mode of oscillation. And so that's why it predicts perfectly why we're seeing this change from the 400-day period to a 200-day period, which is what we observe, in the optical and also in the radial velocity as well. So, is this unique? This was the first thing everyone said. Well, we hadn't seen it in Betelgeuse before. However, when you start looking at other stars in the sky, there are other stars, VY Canis Majoris, which has given evidence of a lot of bits of material here marked on the left by various labels, SWGB, showing that although the star itself we cannot see because there's so much dust around it, we see this material that's been thrown out. And apparently, if you move this material back, you measure how fast it's moving, figure out when did it come from the star, it may have come when the star was getting dim. So it may be that other stars are also showing the same sorts of phenomena, which of course we'd expect. And since then, other stars have emerged, like L2 Puppis 89 Her, and another supergiant in M51. So it may not be unique. I'm glad it isn't, but this gives us a chance to observe sort of up close and personal and see what is really going on. Okay, let's move to the long period. I mentioned that the 400-day fundamental mode is something we think we understand. But in both the radial velocity and in the optical, there's another period, and it's about a 2,000-day period. You see in the top panel, we've outlined that in red with a red curve, the 2,000-day period over the rapidly changing optical magnitude. And then the radial velocity also shows, you see that in the bottom panel in the blue circles, it also shows a long period. Now, lots of people have been debating what that could be. And most recently, there were two papers that looked very carefully at the photometry over a century and a quarter, the radial velocity, the astrometry, and also all the theories that have been proposed, of which there are more than my hands and fingers, my fingers. So more than a century of these both indicate that there is a 2,000-day period. Now, in the left, you can see the collection of, in one of the studies, of the radial velocity in the top panel that covers 120 years, and then the V magnitude. And then on the right, you see the phasing of that on this 2,109-day period. The top shows you the phasing in the V magnitude, and the bottom, the phasing in the radial velocity. When you take all of these data and put them onto you look for a period, and they're both consistent with this 2,000-day period. And both these studies, which just came out in December and January, concluded that Betelgeuse has a companion, and that the companion causes this variation, that the companion has a low mass, somewhere between 2 and 0.5 solar masses, so a little bit more massive than the sun, less massive than the sun. The companion is only 2.5 times the radius distant from the center of Betelgeuse. So that means it's only about 1 stellar radii above the surface, which means that it's plowing through the chromosphere. Now, a companion also explains the rapid rotation of Betelgeuse, because that means that what happens is that the companion can, by tides, spin up can spin up Betelgeuse. And so dynamically, that also answers the question of why Betelgeuse has this rapid rotation. And most importantly, they predicted that the companion should be at elongation. That means the most distant, apparent distance from the surface of Betelgeuse in the fall of 2024, that it should be to the east in the fall of 2024. Well, with something like that in the newspapers, everyone looks. So everyone went to the great observatories to see what they could see. Observatories now have something called director's discretionary time, which means that if there's something that's unexpected, that's important, that's significant, we'll stop everything and we'll go and look. And this was considered to be earth-shaking, important, and significant. So everybody said that's okay. Well, Hubble looked for a spectrum and did not find anything at all. Then the next thing is to go to Chandra. Well, Chandra did not detect X-rays. The contribution there is that it eliminated something such as exotic, like a black hole or a neutron star, which they would expect to have detected X-rays from that. Or some people had even speculated that it might be accreting, much like a T-Tauri star, where it might be accreting material from the wind, and you might see X-rays from the accretion, the shocks that develop in the accretion phenomenon. But a special camera on Gemini North, this, by the way, is Gemini South, but it's just like Gemini North, a telescope on Mauna Kea, just found something. Okay, what did it find? They used what's called a speckle image camera on Gemini North, in which one takes very rapid sub-second exposure, millisecond exposures of an object, and then uses very sophisticated mathematical algorithms in order to extract the presence of an object. And they looked in 2020. This is Steve Howell and a large group of collaborators, and this has been peer-reviewed and published. On the left, you see the image that they obtained in February of 2020. They had just done that during the Great Dimming, thinking that they might see something. They didn't see anything of note at that point. But then, and at that time, the prediction was that there should not be. This should be an eclipse. I mean, this is in a 6-year orbit, 6-year period orbit, and at that time it would have been in eclipse. We should not have seen it. Then they went in December of 2024 and found, as you see where the arrow is, the yellow arrow, found an object. Now, the way speckle reductions work, they're extraordinarily, they're mathematical tour de force, and frequently it produces another image, and you can see something on a straight line on the other side. But they can use other techniques by looking very carefully at the mathematics, at the phasing and what they're seeing, and to determine that that's not real. And the real object is the object which is indicated by the arrow. They also made in December 3 complete independent studies of this. In other words, they made 3 sets, complete sets of observations that all 3 could be reduced separately, and all 3 confirmed to the same level the fact that this object is there. There's also supporting evidence. I put here the press release that NOIR Lab gave out, which is a little bit smooth and maybe a little bit wishful, but it's a pretty picture. There's much supporting evidence for this. First of all, the detection is 1.5 sigma. Now, those who are in the business of making detections are a little unhappy about this. There was a famous professor at Berkeley who had a laboratory, and he had a symbol and a logo, and it said Veritas Duo Sigma, which means that truth is only 2 sigma. So that was generally the feeling in the community. But there's other supporting evidence that, first of all, this companion is at the predicted phase. It's at the predicted angle. We expect it to be in the equatorial plane of Betelgeuse. The companion has the predicted distance from Betelgeuse based on the photometry and the other 2 studies, and the companion has the predicted brightness, which I think gives it more credibility. And they have 3 independent, essentially, measurements of the companion there. They argue that it's more probable than possible in the title of their publication. So what's going to happen? Well, clearly everyone's going to go looking again. What's next? First of all, we are approaching the same conditions and phasing in the 2,000-day period and the 400-day period, the same phasing as the time when there was the great dimming. And so we're all very anxious to look at it again. I have Hubble time coming up in 2 weeks to go back and look to see if this is going to happen again. We don't know, but let's try. And in 2027, that's when the companion should emerge on the other side of Betelgeuse. It takes a while. It's behind it now, and Betelgeuse is big, and so it's not going to be until 2027 when the companion will emerge. So I think people are already gearing up for that. And there may well be other signs of the companion. So stay tuned. We might have more news soon. Don't give up and keep looking. So keep watching. Thanks so much.
Thanks. Thank you, Andrea. That was a great presentation. Sorry, I was having trouble hitting the correct audio button to get myself unmuted.
Okay.
I see that we already have a few questions. So why don't we just jump in? Oh, a couple of them are very, very long.
Uh-oh. I hope I have the answers.
So the first question, and I think I might have to edit the English a little bit. How do we know that the thing that we see, I'm assuming he's talking about that the picture, how do we know that it's Betelgeuse's companion wasn't just mass being expelled from Betelgeuse.
Wasn't just masking. I'm sorry.
It wasn't just like a bubble of mass being expelled from the star. How do we know it's a companion
Oh,
and
oh,
not
oh,
just
oh, oh,
like
it's much more, it's too massive. Its brightness suggests that it's a O or B star. So it's probably comparable or slightly less than Betelgeuse's mass. I should also mention that another thought was that maybe Betelgeuse, moves in the sky, and maybe there was a background star that they just picked up. And so they look very carefully at that, and there's no background star. In other words, maybe it's just brushing by another background star, but there's nothing there. They looked before it moved to that part of the sky, and you can look on sky maps. You can see that there's nothing there, and so it's not that. Yeah.
hey, thank you. Next question says, there's been a bit of back and forth over the last several years about the distance to Betelgeuse, with some citing somewhere between 640 to 650 light years, while others cite between 700 and 724.
That's right. That's right. Yeah, 170 parsecs versus 222. That's right. It depends, I guess, on, I don't know, your attitude or something. The larger distance comes from astrometry measures. The smaller distance comes from modeling. In other words, from doing stellar evolution models and deciding how big it is, should be, and what distance it must be at. So it depends on your which you tend to favor. I personally tend to favor the larger distance because that's a direct measurement. From a direct inference, I should say, from astrometry, which is a measurement. But there is both of them agree that it should be a large star, and again there's some discussion about how large is the diameter 600 times the sun or 1,000 times the sun. Um, there's some tension there. I mean, in astronomy, even the mass of the companion. I mean, in astronomy, we like to put error bars. We do put error bars because there's uncertainty on all these things unless you can go out and measure it yourself. And so there are always error bars. There are error bars on the mass. I mean, like the mass of this companion. I mean, is it 0.5 or is it 2? We really don't know. And so people say, okay, it's 1.5 plus or minus something. And it's the same with the distance. And I agree, there are two distances out there that come from two different methods, and they have not been resolved. It's interesting, people have been looking at, let's say, the Hipparchus satellite, which measured parallaxes, and Gaia, which is measuring parallaxes of millions and billions of stars. It's very hard to measure it like that because of these convective cells. So they move around the star, so it gives you a different position of the bright part of the star. And so therefore, Hipparchus could not measure it, and I think Gaia actually it saturates. So sometimes you get too bright. It's an advantage because we can observe the surface, but it gets too bright for some things, some people to use other techniques.
Awesome. On a very similar note to what you just said, the next question from Rick Dees says, I have read that Betelgeuse is too bright for large aperture telescopes. What techniques are necessary to deal with this?
Okay, you're right. First, you could take very short exposures, meaning that you won't get enough light down to actually, saturate your film or your CCD or something. The other technique, which is being developed a lot now, is what's called coronography, where you place a finger in the view of the telescope, such that it blocks out the bright star. That's what JWST just used. I don't know if you have been following, but it was yesterday, it was just announced that they've imaged for the first time a exoplanet around Alpha Centauri. And they did that by using a what they call coronagraph, which is like a circle that goes in front of the bright star, which is Alpha Cyn, so that it dims the light, so that there blocks it, so that you cannot, so that you can pick up the exoplanets, and that's another technique that you use to do that.
Perfect, thanks. Next up, we have Timothy Weber, who asks, how do you define the surface for Betelgeuse when it has a volume that is significantly larger than the sun's, but only 15 times the mass?
Oh, well, the surface is usually defined as, I use the term photosphere as well, the surface, the visible surface, that what you see in visible light. And strictly speaking, is when the optical depth of the light is the optical depth is 1, meaning that you've got a certain amount of absorption or or across the surface. So that's how the surface, that's how they define the surface. But then the surface is different in different wavelengths. For instance, in the optical, it's smaller than it is if you use an infrared measurement or infrared interferometry or some sort of reconstructive technique. And in Hubble, it's much larger, and it's not really the surface. The term surface is the optical what we call photosphere. It's when you look at the sun, that's what you see. That's the surface. But then it has a more extended outer atmosphere that we can see with different wavelength regions. I hope that's clear, but maybe not. I'm trying.
No, that is a reasonable explanation. I was trying to figure out how I would explain it myself. Because I always hear like tau equals 2/3, right? And I was like, okay, well, what does that actually mean? How do you express that? But yeah, basically, it's just a mathematical way of saying at what point can you not see any further into the star?
Yeah, yeah, yeah.
The next question is from Mike Poxon. He says that mode switching also happens in T Umi, but that was a low mass Mira. Is there a physical link between this and the Betelgeuse phenomenon?
It could be because Myras pulsate. And I don't know that anybody has mapped the surface. As far as I know of that, but it's a pulsating low gravity star, not as big, obviously, as a supergiant, but I'm sure a similar phenomenon occurs. My research has found that people are just, when I had those 4 examples, they 89 Her and L2 Puppis and things like that, those were all supergiant stars, is my understanding. Some we don't know. VY Canis Majoris, we can't see the star, but we suspect that it's a supergiant star. But I'm sure to some extent, when you get these pulsating low gravity stars, they're different from the sun. I mean, that's what was so amazing when we got that first image, that somehow no one had we'd never thought about the fact that it would be completely different. As a matter of fact, Martin Schwarzschild had done scaling from the sun and said there should be thousands of little bright spots on the surface. I mean, so it was just completely an amazing phenomenon that once we got this image, we could see there were these big convective cells, which, as I understand, they're still having problems replicating numerically. But I think, well, I'm diverting from the question, but I think that Myras I'm sure are similar in that behavior. Maybe not as, I mean, they're not losing mass as much, but they are pulsating stars and they are low gravity. And all of that makes for similar phenomena.
So the next question is a bit long. I'm going to try and abbreviate it just a little bit. It's from Christoph Quandt, who is working on yellow hypergiants. And he says that these objects appear to exhibit weak chaotic behavior in their pulsation characteristics, and may also show this long secondary period. He is asking about the state of research on these, what he calls LSPs, or long secondary periods, and could the companion for Betelgeuse be responsible for the LSPs as we see them?
Well, he brings up a good point. There has been work on giant stars and that have long secondary periods, and they have found companions with those stars. Another point which I forgot to mention is that stars with a mass of Betelgeuse, 15 to 20 solar masses, generally have a high percentage of companions. And I mean, it's not 90%, but it's something like 50 or 60%. So it's not surprising that we have good solid evidence now for a companion, prior to the imaging, the direct imaging that just happened. And they have been studied. There's a group who publishes in the Astronomical Society of Canada, I believe, and they've done surveys of giant stars and I don't know about hypergiants, but giant stars, about companions, and that's a fairly frequent phenomenon. Yeah, yeah. It's so interesting. It solves so many problems because one of the things, as I mentioned, was the rotation was puzzling. And so people were working on scenarios where it had been part of a binary system which the primary went supernova and then shot this thing out, into space. There were lots of ideas out there, some more imaginative than others and some more accurate than others too, probably. So, yeah.
Nice. Next up, is more of a philosophical, well, not philosophical, but just he's Bill Dillon is asking, how about using JWST to observe Betelgeuse?
Oh, I know. The JWST, that's what we thought about. The problem is they don't have a coronagraph that would cover the main star. That would cover Betelgeuse. I mean, their coronagraph that they used on Alpha Cen is big. It's like an arc second across. And remember to cut out the light from Betelgeuse. If once you do that, an arc second, you're going to lose you're going to lose the companion because the companion is only let me think, 56 milliarc seconds away from the center of the star, and it's only I'm trying 30 milliarc seconds above the surface. So we're talking milliarc seconds. That's 0.030. and so when you put in a big coronagraph, which is like a finger or a circle or something, you're going to miss all the action. Yeah.
Awesome. Next up, we have a question from Anam who says, if the companion is physically bound to Betelgeuse, is it reasonable to assume that both of them formed together and thus share the same age?
Oh, yes, yes. Yeah. That's the presumption, and of course, when Betelgeuse explodes, bye bye companion, yeah. No, that's what we assume, and as I said, dynamically, it works out. The folks doing dynamic calculations say this is why you'd expect a companion like that would spin up Betelgeuse, and explain why it's rotating more rapidly than we expect. Yeah.
The next question says, would the companion leave a wake in Betelgeuse's photosphere as it moves through its orbit? So I guess the question would be, does the companion's orbit go inside of the photosphere? And if so, what would that do?
Okay. No, the orbit does not go inside the photosphere. It's above the chromosphere. And yes, there may well be a wake. There may well be a wake. There might also be people have speculated that it may be accreting material, but then we did not see X-rays, which is what might expect from accreting material. But yes, there should be a wake. Whether it's fast enough for a bow shock is not clear. My understanding is that it's not fast enough, not moving quickly enough to have a shock ahead of it in the chromosphere. And then it's being buffeted by the wind. Remember, it's only a stellar radius above the surface, and the wind is coming out, and the wind is pretty substantial. So it's being constantly buffeted by that. And I mean, if it were an exoplanet, people would they've modeled exoplanets and that are more distant from their parent host star, and these form wakes around, following the motion of an exoplanet. But it's not in the photosphere. If it were in the, I mean, I think it wouldn't move. It would because the photosphere is dense, and this is in a lower density plasma, but it is there, and we expect that there would be a wake. Yeah.
The next thing is not a question, just an appreciation for a great talk from Tom Bryant.
Oh, thank you.
Next question from John is there a way by which the stellar parameters of the companion star can be inferred with present instrumentation and techniques?
Well, we'd like to detect it. That's one of the issues. Right now, they could get a mass, and he is arguing. Steve Howell was arguing that it's more massive than I would have thought, but he's arguing that it might be like an A star or a B star, and that it then should be producing. It should be at a hotter temperature than Betelgeuse. And one could argue that you should then find some signature of that hotter temperature. The folks who tried looking with Hubble tried spectroscopy to see if they could pick up anything in that area that looked anomalous, and their predictions said it was, I don't know, 50-50, because you know that from this hot plasma you find certain ions, and they were looking specifically for these ions, carbon-4, nitrogen-5, things like that, and they didn't see anything. So they haven't seen that. Clearly we ought to try looking for some kind of continuum, possibly, and they've done that with IUE ages ago, but I don't know if they've done it at the right phase to see that this is where you should see it. It's very tough because Betelgeuse itself is variable. I mean, when we look at one side, the east side is different from the west side, and the surface creates all sorts of different background fluxes and levels and line strengths. So it's not like you're looking at a isothermal, nice, smooth surface. It's different from one side to another. And so you have to then to see if you can separate out what might be coming from this companion and what's happening to Betelgeuse. But I think people are thinking of lots of things, and I'm sure I haven't thought of everything that's possible.
On the subject of the companion, Edgar asks, or he's assuming that the companion would be a hot young blue star, and he's asking why that would be the case. I don't know that there's anything to suggest that it would be a hot young blue star, unless maybe there was something in your talk that would suggest that. I don't know.
Well, Howell, the Gemini observations indicate they came out with a higher mass than came from the velocities and the visual magnitudes. They seem to suggest that it would be an A star. We suggested, I was working with Morgan on his analysis, and that it should be more like a K star, like cooler than the sun. cooler than the sun. So there's still, as I said, this is the uncertainty that trails all astronomical observations. But this is something to try to sort out. Yeah.
Awesome. Next up, Jose asks, has any attempt been made to calculate the orbital motion of Betelgeuse's companion? And I would say probably yes, and
Oh,
that the
yes.
answer
Oh,
is
yeah. Well, it's right now. Yeah. It's just, so right now they're assuming a circular orbit, and that's what the velocity seems to indicate. It's a circular within the error bars. Okay, that it's a circular orbit, and that it's most probably in the equatorial region of Betelgeuse. In other words, that it's where it's perpendicular to the poles. So it occurred where we expected it to be, because the pole is angled about 42 degrees east of north. And so you take that, and then you put your equator 90 degrees from your axis, and that's where the object was found. So it fit nicely, and the distance was reasonable. So that gave, I think, the Gemini folks, more confidence. One more point, giving them confidence in their result.
Next up, we have a question about the speckle imaging from David. I don't know that you're going to know the answer to this, so I will ask, but I think he's basically saying that the speckle images from the 2020 and the 2024 observation were taken at different wavelengths in different wavelengths.
Yes,
He's
yes.
asking if that would cause a problem, and I guess the idea is like it's not a one-to-one comparison. So,
That's right. But people feel that it wouldn't be visible in one and not in the other, just because of wavelength. I mean, in other words, there's no object that would just produce emission at 5,000 but not at 4,500 angstroms. That sort of thing. Yeah. Actually, you see, there's a history with speckle. The history is that I think it was 2008, other folks used a speckle camera and said they detected a companion to Betelgeuse, and that was never confirmed. It wasn't in the right place that's consistent with these measurements or these predictions, these models. And it was never confirmed. Several other people went looking using different cameras and so forth, and it was never confirmed. So speckle, I think, was very undeveloped at that time, and they probably gotten better at analyzing it. But it's a real acrobatic effort with mathematics to produce that image. But the fact that their experience, they've done it. They did it with 3 independent data sets taken in December that reproduce it, gives them more confidence, even though it's 1.5 sigma.
cool. So we're coming up on 15 after the hour, so I'll take a couple of more questions. And unfortunately, the line for the Q&A just keeps getting longer, so I'm probably gonna have to cut it off after that. But next question is, thanks for this amazing and enthusiastic talk. Will the presence of a companion make astronomers reinterpret some older data of Betelgeuse?
Well, people have been looking at older data to see what, I mean, I've even gone back to my old, we're all looking at our data. I think it's true. It's sent people back to looking at the data. I think we'll look more carefully at the IUE data, which had a lot of analyses on the continuum and the detection or not of the continuum. No, it's really inspired a lot of, yes. Astronomers are always anxious to find evidence, absence of evidence yet, but may not be for long, So, yes.
Next question is there a preference for photometric filters in the upcoming observation season for us observers?
Uh, No, I mean we've been extremely happy um, with the V and the B measurements, photometric measurements are very good. There's also uh, well, there's also, I was thinking of these meteorological satellites. There's a wealth of data in the NOAA GOES database, which has never been accessed. We got them to change the format so we could read it, but there's a lot of information there because, and that's particularly valuable when if we could put it with the Himawari data, because then we get better signal to noise, and that's where they have 16 bands. So, and they even have, molecular bands. So you can see what the molecules are doing. And this is every day. I mean, this is just a treasure trove of material that could be analyzed. That's exciting. But no, we are very happy with the photometry. Of course, I always love spectroscopy, but the photometry is great, and I go practically every day to the online website for the AAVSO to see what's happened to Betelgeuse.
Nice. Okay, I think this is a great question to finish it out on. Melanie asks, how long have you been studying Betelgeuse?
Oh my goodness. Well, how long? 1987, maybe? I haven't thought how long that is. More than my fingers and toes, I think.
That would be
We
30.
started with IUE, and that's where we found we could look at a lot of the ultraviolet variation, and we could find how we knew things were happening in this extended atmosphere. And so that was what really started me on Betelgeuse. And it's been fun ever since. That's what you have to have. I mean, you have to really like what you're doing and be driven by the quest for finding out what's out there.
That's great. Okay, I think that is all that we have time for today. I'd like to extend a very heartfelt thank you to Dr. Dupree for sharing her time and knowledge with us today. I just have a few things to finish up. Again, I'd like to thank this webinar sponsor, Boyce Astro. They have sponsored our entire 2025 series. Boyce Astro provides online astronomy education, observatory researches, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out our website. Please check out their website at Boyce Astro to learn more. If you enjoyed today's webinar, please consider a donation by scanning the QR code on your screen or going to aavso.org. All donations are tax deductible and enable us to offer educational opportunities like this one free of charge. As a reminder, registration is now open for next month's free webinar. This one scheduled for September 6th, and we're expecting a fascinating time with Dr. Karen Collins, who will talk about the TESS follow-up observing program. So if you want to learn about confirming exoplanets, this is the place to be. Finally, I wanted to do a small plug for our annual meeting, which will take place in November 1st and 2nd at the Museum of Science and Industry in Portland, Oregon. Please scan the QR code or visit the URL to learn more, and we hope to see you there. Finally, thank you all for attending. You have been a wonderful, large audience. There will most likely be a survey after this that we would love for you to fill out. And if you have any further questions, please feel free to email me and I will try to pass them on to the appropriate.
Okay. Listen, you've been a great audience too. It's been fun.
All right.
Okay.
Thank you all, and I will see you later.